So welcome to the Network Service Mesh Deep Dive. So this is where we pull back the curtain and show you the spider running the show. So if you haven't met us, I'm Frederick Kautz. This is Ed Warnicke. And let's begin.
So, a couple quick things. If you have questions, ask them as we go. Because if you have a question, somebody else in the audience is going to have that question, and you do everyone a favor when you ask it. So that's the first thing. The second thing is, I will be asking you questions in the course of this talk, and asking you to raise your hands just to get a feel for what's going on out there. And it's always good when doing these things to calibrate first. So, quick show of hands. How many of you can raise your hands? Excellent. Cool. Now, there's one other interesting thing I want to know, because I got caught a little off guard with this the last talk when we did the intro. How many of you are sneaky network people? Ah, okay. More than I expected. Cool. And how many of you are app people? Excellent. We got a good blend here. Good blend. Very, very cool. Now, how many of you guys made it to the Network Service Mesh intro talk? Okay, that helps, because this is the deep dive. We showed you how easy it is to use and how conceptually simple it is last time. As Frederick said, we are going to pull back the curtain and show you the spider pulling the levers behind.
Great. So some housekeeping. So you can reach the Network Service Mesh KubeCon events page from this particular link. We're coming to the end of it, so we have only a couple things, only a couple events left. So, but go ahead and take this. This will also take you to the Network Service Mesh website, so you can see our slides and other material that we prepared.
Yeah, one other thing to keep in mind, we will not be doing a demo this session because this is the deep dive, but both Frederick and I still have demos that we're doing in the Red Hat and Cisco booths respectively. So if you want to get a little bit more of an intro and a little bit more of a demo, those are probably good places to go get it. Cool. So the next piece of housekeeping, if you want this slide deck, that will take you to this slide deck. It's on Google Docs. I know people are often asking, where do I get this slide deck? This is where you get this slide deck.
Highly recommend this one. So you're going to see a lot of good information on here on how it works, and so make sure you get a good picture.
Cool. Everybody good? 3. Oh. By the way, for those of you who give talks, nothing beats QR codes for getting an entire audience full of people holding up cameras. All right. Going once, going twice, and here we go.
Great. So the problem. What is the problem?
So the problem is that we've got people who want things that look like this. This is kind of what your app developers want. They want something where their pod is running, it does its thing, it's normal Kubernetes networking, but maybe you need something a little bit more, something that Kubernetes networking doesn't provide. In this example, it would be secure intranet connectivity. And you don't really want to think too much about that. You just want it to work, and you don't even want to know what security is. That's what you have NetOps people for.
So this is what it looks like in terms of network service mesh. So you saw this particular slide before if you came to our intro. So you have a network service. You have the connection. So if you notice Sarah's pod, all she sees is the L2, L3 connection to the network service. Everything in the cloud is a cloud to her. So she cannot see what's inside that cloud other than the fact that she's getting her service. But as you can see inside the cloud, we've actually chained firewall pod, VPN gateway, et cetera. So we provide a nice, easy way to abstract this, but also still get you the details that you need.
So, really quickly, on to the solution. So, the solution is, this is the link to the Network Service Mesh intro deck. We will do a really quick run through of some basics here just to set the tone, but we spent an entire talk talking through how this looks and is simple to people who consume it, how it looks and is simple to people who operate it, and all the rest of it. If you actually go behind the curtain to see the spider pulling the levers, it's a lot more involved. But we're going to do a really quick hum a few bars version here.
Great. So a couple things to notice. We have a firewall pod that has a label, app equal firewall, and we have a VPN gateway pod that has an app equal VPN gateway. So these are how we know what pod provides which particular aspect endpoint of that service.
Exactly. And then if we get something like the firewall pod, so the firewall pod exposes the secure internet connectivity service, but it also consumes it. And this is super helpful because it means your firewall pod can be dumb as a rock. Because all it knows is it's applying firewall rules, and there's going to be somebody who comes after it who handles other aspects of secure internet connectivity. What those are, it doesn't know or care. But how it hints to us so we can apply policy is when it asks for an L2 or L3 connection to the secure internet connectivity service, it puts a label on that request that is app equals firewall.
So, yeah, so a rock that can act as a firewall. It's a pretty smart rock. And so this is what the definition looks like. So you see we have a match. That match, the source selector is app firewall, and the destination is VPN gateway. So when it connects to its own service, secure internet connectivity, then this is the definition that that tells it where to go. And looks like Ian has a great question.
Ian, you have a question. Oh, this file can be written by the app developer if they're the ones deploying the network service endpoints. It can be written by some NetOps person who says, here is a YAML file in some containers if they're the ones putting it together. It's just like when you put together services in Kubernetes. There are many people who may provide those services. It becomes a question administratively internally of who produces it.
But then the question I asked you really is, Sarah here, you say doesn't know anything about the cloud block.
Correct.
This describes what's in the cloud block, so it's not Sarah that writes the cloud block. He gives it to her.
Probably. Cool. And then the question becomes, how do we connect Sarah's pod up, the sort of general consumer who's not part of providing the service? And in this case, you have a match. It matches anything that falls through that doesn't actually have labels on it. And the match has a route that says, okay, connect this to something that has a label app equals firewall as destination labels. So that's the hum a few bars version. Now we're going to dive into the architecture. Everybody still with us? Show of hands. Awesome. Cool. So there are kinds of there are two ways to abstract problems in general. One is you can focus on the implementation. This is kind of what happened in Cloud 1.0. We took all the physical things in the world and we slapped a V in front of them and we called it good. And this had one really, really nice characteristic and a bunch of really bad ones. The really nice characteristic was nobody had to rethink anything. You already knew what interfaces were and subnets were and everything else. And so it was kind of familiar-ish. The second way you can do it is to be developer-focused. This is very much the way that Kubernetes has gone. It focuses on what exactly is it that you need as a developer. So when you look at how this applies to things like adding additional networking services to the world, if you were to do this in a way that's implementation-focused, you would start adding virtual interfaces and virtual subnets and all kinds of things. But the truth of the matter is, that's not actually what developers generally care about. Every now and again they do, but generally they don't. What they care about is, number one, they want to get their normal Kubernetes networking services because the normal Kubernetes networking is awesome for what it does. And if you need more than that, what you really want is to be connected up to something that functionally does the things you need with the other packets or frames that you're dealing with. And those things may be things like connectivity to isolated resources, protecting you from threats, allowing you to talk to various things, load balancing, QoS, etc. And so if you look at this, it's not any one of these things that you actually want. It's some Venn diagram of them. And that intersection of the Venn diagram is actually what we call a network service. And there are still interfaces and subnets and all these implementation details there, but rather than making you cobble them together with 1990s networking concepts, we abstract them to the thing you care about.
Okay, so we got 3 easy pieces. Easy peasy. So first is the actual network service itself. So you've seen this in the intro slide that we had before. So the network service is the thing that the user wants. The network service endpoint provides that particular service or a portion of that service. So that could be the firewall or VPN gateway. And then you have the connection that connects you to that particular implementation of the service that you want. So keep those 3 ideas in mind because we're going to be making use of them extensively.
Yeah. And it's important to realize when you deal with an L2, L3 connection, the payload it is carrying is an IP packet or an Ethernet frame, or for the more exotic among you in the audience, the sneaky network people, maybe an MPLS frame or something else more exotic.
Yeah, and just for clarification, so for those of you who are looking at Istio and saying, how does this compare to it? So Istio is L7, L4, so you're working with application HTTP through a stream. That stream would be TCP. We're looking at L2, L3, so we're looking at IP, MPLS, or various other payloads. And so very, very...
And to be clear, an Istio-style application service mesh will run just fine over a network service mesh. It'll never know we're here. And honestly, we will never know that it's there either, because it's way over our heads.
So the abstract components. So to start off with, we have what we call a network service registry. And so the network service registry is composed of what network services are present, what are their endpoints, and so the endpoints are the pods and so on that we showed before. What are their managers? So in other words, I have an endpoint. Which NSMD is the manager of that? And
we'll be saying a lot more about network service managers in a moment.
Exactly. So the way that this looks is, so this is actually a proto BoF. And so we provide a network service. The network service has a name. It has a payload. So the payload being IP, Ethernet, MPLS, GRE, or VXLAN, or so on. And then we have something that matches. So those are the matches that you saw before. The network service endpoint also has a name. It has a payload as well. It has the name of its network service manager. And again, we'll come to more on this in a while. It has the endpoint name. It has a series of labels, which is used to provide information about that particular endpoint, and a state, like is it up or is it having trouble?
Cool. And then the network service manager is the final one. And again, we'll say much more about network service manager shortly. But effectively, a network service manager has a name. It has a URL, which is how you talk to it if you need to talk to the network service manager. And it has a little bit of information like, okay, did we actually hear from this guy recently? Do we know he's still there? Do we have a state for him, etc.?
Right, so every network service manager, I guess we'll call it a domain in this scenario, every node has a network service manager.
Yeah, so we're going to talk about this first in the abstract. Then we'll talk about it concretely in Kubernetes, because it turns out that whenever you have a network service registry, there is some domain of network services and network service endpoints and et cetera that it encompasses, right? We call that the network service registry domain. Every time you have a network manager, there is some domain of network service endpoints, network service clients, and data planes that it's actually managing. And we'll see concretely what this means in Kubernetes shortly. And of course, you could have any number of network service manager domains that are filling into a network service registry.
And in this scenario, take note that, so imagine that this is a Kubernetes cluster for a moment, right? So there is one network service registry. So multiple network service managers that will publish to that registry and will read from that registry to work out where their network services are coming from.
Yep. So now, important things to realize. So different network service managers will advertise the network service endpoints that they have to the network service registry. This is the only point of centralization in the system. And then the network service managers will communicate with each other peer-to-peer to set up the L2, L3 connections.
So for the Kubernetes version, so the network service registry itself is implemented and makes use of CRDs. So it's an application that makes use of CRDs. And so basically all of the status where network service endpoints and so on are stored within those CRDs. And we pull from them. And so beyond the network service registry, everything else is done orthogonally.
Yeah, and this is super nice because then you can say, okay, well, kube-control get NSE. And you'll get from Kubernetes the list of network service endpoints that it's got from the registry, because we're using these custom resources in Kubernetes in the API server. And then the network service manager, it's noted there, is running as a daemon set on every single node. So every node is a network service manager domain and has a network service manager. And of course, you also need to run some kind of a data plane to do your cross connects. And this can be any number of things. Network service mesh is completely agnostic as to what you plug in there as a data plane. We do provide one, But if you don't like it and you want to do your own, as you'll see a little bit later in the deck, the API that has to be exposed if you're a data plane is dead simple. Mostly because we don't ask you to do very much. Yes? Network Service Mesh, and you'll see when we get to the data plane API, it is speaking an API that specifically asks for the creation of cross connects, and your vSwitch would expose that API so it can create the cross connects. But you'll see that when we get into the API in a bit.
Great. So the next thing is we have network service endpoints, and so in Kubernetes, these all end up as a pod. So if you saw the demo that I gave before with the bridge domain, that bridge domain was then deployed as a pod.
Yep. And then you also wind up with network service clients. These are pods, like Sarah's pod, that want to be connected to a network service. And again, they end up talking to their local network service manager.
Okay, so all
Now we begin drilling into the API.
so
How many people like APIs? Oh, good.
I should have raised my hand because I do like APIs. So all the purple edges you see here are gRPC. So just so you know. So we're going to start with the network service endpoint registration. So the registration message has a network service manager, and the endpoint as well. And so what happens is the endpoint will call register NSE and say, I'm exposing a bridge domain, or I'm exposing a firewall, and will notify the network service manager that it is ready for connections.
Yep. And then the network service manager will do a few things. It will basically, make sure the network service manager references itself because it's the one in charge of that. And then it will translate this to the CRDs that are going into the API server and go stick them up in the API server so that when you do kube control get NSE, you will see that network service endpoint listed.
So the next part is the node as well. So the client will ask for a network service, and so what it does is it creates a connection object, and it specifies the mechanism. So the mechanism is where you ask, I'm looking for a kernel interface, I'm looking for a MEMIF or vhost user, and so you can see in the service we do request network service, and the response is going to be a fully specified connection. And part of the reason that we specify the connection here is you may have partial parameters that you may want to
There may be
specify.
some partial things you care about the connection that you may put in there.
Like you might want to know what is the interface name going to be, as an example.
Yep. So one thing to keep in mind here is these are local connections. So one of the distinctions we make in network service mesh that's super helpful is if all I really want to do is get an Ethernet frame from here to there, how many folks actually want to be forced to deal with how it gets there? Not saying you can't, but want to have to. No choice. Who keeps inviting the sneaky network people? So what network service mesh does is it allows you to specify what kind of local connection you want. Now, for a normal application, like somebody who wants to just be connected to secure corporate internet connectivity, you're just going to want a kernel interface, dude. You really don't want anything hard or complicated. You just want to run your damn app. But if you're writing a network service endpoint, or you're doing NFE and you're writing a CNF, you probably want to use a higher performance mechanism like MEMIF, and we will allow you to specify that as the thing that you want, and we will give it to you. So you do have options. But the things you don't see in a local connection are things like VXLAN, GRE. These are remote connection mechanisms, not local ones. Now, obviously, if you're passing Ethernet frames or you're passing IP packets as payload, you can put those things in the payload. That's awesome. But you don't deal with that in terms of getting from pod to pod. Yes? Yes.
Yeah.
Absolutely.
Yeah.
It's purely scoped to the connection, not to the pod.
Yeah.
The question was, could he have a single pod that asks for one network service with a kernel interface and a different network service with a MEMIF? And the answer is yes. The mechanism is scoped to the connection, not to the pod. Other questions? Very cool. And this drills down a little bit more into what goes into a connection object, right? So it's got an ID. We put the information about the network service it's a connection for in there. And it actually has a mechanism, and we'll talk in a second about mechanisms. And then there are two interesting things here. One is the labels, and we've talked about how the labels get used for all kinds of cool things like routing. But we also have in here a set of values that we call the connection context. Now, connection contexts are cool. Mechanisms get negotiated between you and sort of the next hop in your system, right? Like, I need a kernel interface. I need a MEMIF. The connection context is negotiated between you and your network service endpoint. So, for example, if I need a source IP, that source IP is coming in the connection context from my network service endpoint. If my network service endpoint wants to make sure that I have routes that point to it, say I'm a VPN gateway and we want routes for the corporate intranet, that comes back from my network service endpoint in the connection context. Now, the rest of the system will simply pass this on through, but it's a crucial element because there are lots of these fine details that you don't want to actually deal with if you're the consumer generally, but you want to make sure they happen. Then for mechanisms, we talked about different types of mechanisms, and depending on the type of mechanism, they'll have parameters. If I'm asking for a kernel interface, it may have the interface name. If I'm doing MEMIF, there'll be a socket file name. Those kinds of details. And then you do get mechanism types. We talked about how you might get a kernel interface if you're a normal everyday application. You might get a MEMIF interface, or an SRIO VNIC, or a hardware interface. These are all mechanisms from our point of view that connect you to a network service.
Great. So the next part is the actual network service request between the network service manager. So when you're crossing between node to node, then what we do is we have the connection and we pass the connection on, but we also add in some additional information into that. So if you notice, the network service request is pretty much the same API as the client to the NSM daemon. But NSM daemon to NSM daemon, we also include other information like let's see, do we have a slide on that?
We do.
So it also includes information about what do I support VXLAN, or my data plane supports VXLAN and GRE, which one, and with these parameters, and pass that on to the remote side. And so what you can see is we have mechanism types. So you can see like VXLAN, GPE, GRE, etc.
There's no end to the creativity of the folks in the IETF. This list will grow for all of time. I'm sorry, we can't make them stop. But here's the thing. You never have to know. The guy writing an application pod never has to know again what the hell these things are. If you're writing a CNF, you never have to know. When all the people who were beating down your door last year telling you you have to have MPLS over GRE show up again and say, no, that's not good enough anymore, we want MPLS over UDP, you don't have to rewrite your CNF because that's all handled by the network service mesh.
Yeah, and so this mechanism type, this remote mechanism type, is added by the NSM, and then it is stripped by the remote NSM side as well. So the client and the endpoint never see the remote mechanism information that is being used. So it is strictly encapsulated and stripped on the other side, keeps the connection and what they have to worry about very simple.
Yep. So this is sort of the big picture here where we see all the different steps. And the last one is when the network service manager on the remote node goes to talk to its network service endpoint, guess what? It uses exactly the same network service API that the client used to ask the network service manager for that connection. So it's the same API, it's the same parameters. We've got a remarkably small number of APIs, and many of them look very close to each other. So the system is very, very simple. So now we're going to talk about how you interact with the data plane. You may recall that I said that we're really super agnostic about the data plane. The network service manager does not actually program your vSwitch directly, because that would weld us to a particular vSwitch. So for example, a lot of the folks in Network Service Mesh really like VPP because it's a super performant, super easy data plane to work with that does everything. But we don't directly program VPP. Instead, what we have is a data plane API. And that data plane API is pretty simple. It has a streaming RPC called monitor mechanisms that allows us to find out what things the data plane can do. This data plane can do SRv6 and VXLAN. So if someone asks me for MPLS over UDP, I'm sorry, that's not something I can do. And it's got very close semantics to what we've seen before. I can request a cross-connect, and we'll see in the next slide what a cross-connect is. And I can close a cross-connect.
You've just exposed my demo and why it was so easy for me.
And exactly. That's exactly why it was so easy. And so what a cross-connect is really flipping simple. A cross-connect is two connections, a source connection and a destination connection. So if it turns out that the network service endpoint that I am talking to is on the same node that I am, then it will be a source connection that is local and a destination connection that is local. If it turns out that I need to go to a remote place, it will be a source connection that is local and a remote connection that is the destination. And if it turns out that some other NSMD has asked me to connect to an NSE for it, it will be a remote connection for the source, and it will be a local connection for the destination. But semantically, all you're ever dealing with in a cross-connect is two connections that you are cross-connecting, meaning whatever IP or Ethernet comes in one side, you send out the other, and vice versa. Everything is point-to-point. So a really good way to visualize this topologically, and I'm going to stop and do cartoons for a second. From the point of view of the network service client, all it sees is this little green line that is a local connection. And then magic happens in the cloud in the middle. And from the point of view of the network service endpoint, all it sees is this local connection that magically packets and frames come to and from on. And that's all you see if you're the network service client or endpoint. If you drill down into the world the network service managers see, what you discover is there is actually a data plane next to the network service client and a little yellow diamond that is the cross connect that takes you to a remote connection. Now this is the same, literally the same remote connection object on both sides. And then a data plane that cross connects that to the local connection for the network service endpoint. Now, again, I promised you cartoons. How many people like cartoons? Everyone likes cartoons. Cool. So imagine that we have a happy packet. All of my packets are happy. It starts in the network service client. Maybe it's an Ethernet frame or an IP packet. It goes into the data plane. The data plane cross-connects the packet from the local connection to the remote connection, where it probably picks up an encapsulation. It goes through the network, and it arrives on the other end of that remote connection, where it gets decapped by the data plane, gets cross-connected to the local connection to the network service endpoint, and then it arrives there. So that's the extent of my cartooning skills, I'm sorry. But it's a happy packet. And of course, this works the other direction as well. So these are the APIs that we've talked about so far. We've talked about how network services get registered, how they get requested, and then how the network service manager talks to the data plane. Now we're going to talk about monitoring. Monitoring is fun. So for all of these objects that we talked about, we have streaming gRPC APIs that let us monitor them.
Right, so in the monitoring, so you can see that it has a initial state. So we're going to transfer initial state as to what's going on. We have an update and a delete. And so the the monitor is it will effectively give you information about what type of cross connects that it currently has. And so this is particularly useful because if you're an NSM monitoring your data plane, then you can ask it, like maybe your NSM dies and then it comes back up. You can say, give me the initial state transfer, so now you know what the data plane knows, and then you can then continue to get updates in a very simple way. And so we try to keep this as simple as possible, and this API is also what we are able to use in order to hook in things like Skydive to work out what is going on within my network, which is what you saw if you came to the initial demo. That's what drove the UI that we had. So.
Yeah. I mean, effectively what it comes down to is your network service manager has a really strong interest in knowing what your data plane believes the state of the world is with regard to cross-connects, because the network service manager doesn't actually touch packets. And the monitor cross-connect call lets it know in real time what actual state is there in terms of cross-connect state. So there's the second set of state you might care about is connections. Now, most network service clients are kind of dumb as a rock. They're going to have an init container that runs, sets up their network service connections, and then exits and the app runs. So most clients are not going to call monitor cross connect. for their monitor connections for their network services, but they could. And we would tell them the state of the connections that they have. So if something goes wrong with a connection, they get informed. And then for remote connections, it actually gets to be super important because you've got two network service managers. They really, really want to know the state of the connections that they have between each other remotely, because that actually lets them know the health of those connections. And as we will see shortly, we can do really cool stuff with that, like auto heal. And then, of course, when we get to the far end, the network service manager can use exactly the same local connection, monitor connection API to see what its network service endpoint believes are the connections in their states. So the monitoring ends up looking like this. And now we come to the harsh reality of life. Pods die. In fact, pods are designed to die. The entire point is that they're disposable. But it turns out that in network service mesh, every bit of important state in the system, you share with your neighbors. So the local connections, the cross connects, the remote connections, all of these things are being shared with your neighbors. And in fact, in the case of cross connects, you have information both on remote connections and local connections in those cross connects. So if the network service mesh manager dies, it can relearn from its neighbors the state information, not about what it scribbled down in some database before it died and the whole world changed on it. No. It can find out in real time exactly what's going on in the world and reconstruct itself and start operating optimally again. Now, the other thing I'll mention is, as Frederick mentioned, the monitor cross-connect is the same API we expose north from the network service manager, so things like Skydive can do monitoring and topology.
Great, so auto healing. So I have a VPN gateway pod, happy packets going through. Suddenly my L2, L3 connection between my firewall and gateway dies, or the pod dies itself. So now we have unhappy packets, or do we? No, we can actually reroute you independently to the other VPN gateway that's on there. And without the firewall pod having to do anything, it doesn't have to be even aware that the VPN gateway pod went down.
Yeah, so keep in mind, the local connection from that firewall pod to the data plane is still good. So all we have to do is update the cross-connect to point to a different network service endpoint, and everything is good. So what death of a network service endpoint looks like in network service mesh is a brief network connectivity blip, followed by everything being okay again. How does what? So here's the deal. There are some things in the network service that have state. If you are stateful, we have made your life no worse by auto healing for you. Right? So you're absolutely right. Stateful network services are kind of interesting, particularly since one of the things we don't have in the picture that we're mulling is the same thing that lets us auto heal also gives us mechanically the ability to update the graph dynamically for existing clients if you change policy. Now, if I do that, I very well may make things worse than what they are right now. So there's a question about what the wisdom is there. But for auto heal, you're never going to be worse off. So we're almost done. So remember we talked about the 3 easy pieces. So 3 easy pieces plus 3 implementation details gives us 6 easy pieces. Right? So these were the initial 3 easy pieces. Network services, network service endpoints, L2, L3 connections. Then we added network service managers, cross connects, and monitoring. But again, it's very simple. Almost everything is just request, close, and monitor. So really quickly, we're going to go very fast because we're almost out of time. To K8s and beyond. So we talked about this abstract picture. There's a reason I talked about the abstract picture. And it's because when we project out into Kubernetes, we can actually imagine a world where you have network service managers that are external to Kubernetes, that are actually registering network service endpoints from the outside world into your cluster. And then your network service managers can in exactly the same way talk to them and get your cross connects. So you could imagine a second cluster doing this. So now you've got cross-cluster behavior for cross-cloud. You could imagine an ENSM for an existing OpenStack or VMware Vim. You could even imagine getting network services from your physical network. So, proxy network service managers, PNSMs. So, These are really fucking dangerous people. Seriously. They are the lightsabers of the NSM world. They can cut through anything, and if you are not strong in the Force, you will cut off your damn arm. So with great power comes great responsibility. But it turns out that you can literally put together a proxy network service manager that is pretending to have network service endpoints that it does not have. It has no network service endpoints, but it advertises them. Say, advertising one with app equals physical hardware, because you want some kind of fun thing to happen in your physical network. And you can put in policies that basically hijack the request for your network service to your proxy. Your proxy gets the remote network service connection request. It looks at it, possibly munges your physical network, possibly munges the request, and it turns to someone who actually really does have an endpoint. When the response comes back, it can possibly munge those parameters, and you wind up with an L2, L3 cross-connect here. But in the middle, you may have changed your network. You may have slightly changed the remote connection. So for example, if you're doing SRv6, you may have added SIDs to the SID list to do traffic engineering. All kinds of interesting things can be done this way. Not all of them are a very good idea. In fact, a great many of them are a terrible idea. But some of them are brilliant. All right, I think we are actually out of time. So if folks want to talk, I will walk out into the hallway with everyone else, and I would be happy to answer any and all questions, and I'm sure Frederick would as well.
Absolutely.
Thank you.